Hi, welcome back to my channel. For today's video, we will be talking about the introduction to group theory. So for those who are new to my channel, please don't forget to subscribe on my little channel for you to get educational yet fun and exciting updates in mathematics in all levels, depending on your request. So for today, I am finally giving a respond to the request to create a video for group theory. So thanks for those who messaged me on my Facebook page, and I appreciate that. So what is group theory? Well, group theory is actually a study of algebraic structure known as groups. So what is group? So typically speaking, for a group, it is actually the modification in the sense of symmetry. So suppose we have a picture like this. Assuming that this picture has a symmetric face, feeling guapo, charot. If I'm gonna flip it, like rotating with respect to the line passing in between today's face, it actually look exactly the same. So it is a statement about an action that we can take on that picture. So similarly, let's consider a snowflake. So it is symmetric and even more symmetric in different ways. So we can flip it in different various axes. Okay, so a collection of taking all these action that happens on this snowflake will leave it together like a group. So the take on different actions, even the one we do nothing at all, or just like taking the picture and do nothing at all, have different fancy names. Like we can have it like D6, K4, or whatever. But in this video, we only focus on the abstract discussion of the group. Okay, so let's start with a formal abstract discussion of a group. So a set G, together with a binary operation in G, is said to be a group if it satisfies the following property. So first is associativity. That means for you have this one, we can have this is just equivalent to this. So you can regroup, sort of. So that will hold for all the elements in G. Also, the existence of identity. So that means we can find an element E in G such that for every A in G, we have AE equals EA, and that's A. Okay? And of course, the existence of inverse. That means we can find an element, the inverse A in G, such that the binary operation of A and A inverse is equal to A inverse A, which is equal to the identity that holds for all element in G. Okay, but these three are actually criteria for us to identify if the set is G. But first things first that we have to remember before we check on the three criteria is that G should be closed under the binary operation. G is closed. Which means to say that if A and B are in G, then the binary operation of A and B shall also be in G. That's it. Okay, so now the things that we have to remember, because we want to make sure that for a set to be a group, we have to make sure that these three conditions, along with the closure property, are satisfied. If only a given set only satisfies A, so if only A is satisfied, G is just a semigroup. So if only this A here holds. Now, if only A and B are satisfied, but there's no existence of inverse, so G is not a group, but a monoid. So just to make sure, if three conditions are satisfied along with the closure property, then that is a group. But if only condition A is satisfied, then we only call that set as a semigroup. If only two conditions, the first two conditions, associativity and the existence of identity, then that G is a monoid. So, which means to say that the given set G as a group, we can call that as well as a semigroup or a monoid. And a monoid, we can consider that as a semigroup, but a semigroup cannot be considered as a monoid, nor cannot be considered as a group. Okay, that's it. Now, since we have to make sure that three conditions shall be satisfied for us to call this as a group, if three conditions are satisfied with additional property that for every A, B, and G, G here is a group. AB is equal to BA. So that means there is a commutativity property exists in that G, then G is a abelian group. So G is a abelian group or a commutative group. And last, that we have to remember for one terminology that we consider in this group is that the cardinality of G is what we call the order of G. That's it. Okay. So the set of integers equipped with addition is a group. So if you're wondering why, so we will prove on that. So first things first, before we consider the three conditions, let us make sure that the closure property holds. Remember that if you are given with two integers, the sum of two integers are always always element of the set of integers, which means z is closed under addition. So that means closure property holds with respect to addition. So for you to be able to visualize on that, let's consider integers. Let's say 5 and 7. So this is not part of the proof. I'm just showing you an illustration. 5 here is an integer, 7 is an integer, and if you add that, that's gonna be 12. 12 is an integer. That's it. Okay, now let's double check if it holds with the first condition, associativity. So for every A, B, and C in Z, that means you have three integers. So A plus B plus C, it doesn't matter. It will still be the same if I'm gonna regroup that. That's it. So therefore, this implies that Z is associative. Okay, now let's how about the existence of identity? So remember that 0 is an element of Z. And for every A in Z, if you're gonna add A by 0, that's the same as adding 0 by A, and that's still the same A. So therefore, identity element exists, and 0 is the identity element. Okay, so let's check the last criteria. For every A in Z, observe that the negative of A is also in Z. So let's consider, for example, you have 5. You pick 5 from Z. 5 is an integer. Negative of 5 is negative 5. That's still an integer. So therefore, A, the negative inverse exists in Z with the one You add A by negative A, that's the same as adding negative A by A. And if you add these two, you get 0. So therefore, the inverse element of A exists. That's it. So we can tell now that Z is a group. In fact, this is a billion group. Why? Because if you pick two elements, let's say A and B in Z, remember that if you add A and B, that's the same as adding B and A. Let's say you pick two numbers. You have 4 and 3. So if you're gonna add 4 and 3, that's gonna be 7. If you're gonna add 3 and 4, that's still 7. This simply tells us that 4 plus 3 is the same as 3 plus 4. So we can say that the commutativity holds in Z. And so Z is an abelian group. That's it. Since we are talking about the abstract discussion of a group, in fact, the basic abstract discussion, then I'm going to provide you the properties. These properties are actually theorems and are pretty basic, present in the study of the group theory. Number one, the identity element of a group is unique. So why? So if we are interested why, then let's say suppose there exists another identity. Let's label this as A prime. So let's call that as identity. Remember that E, I can write that as E prime. Why? Because this is identity, so this is also element of G. So if you multiply an element by an identity, you get the same element. But if this is also identity, so this can also be the same element with this. So that makes sense that the identity element of a group is unique. Number two, the right and left cancellation hold. What does it mean? Suppose you have elements here, A, B, C, and G. AB will tell you that if that's equal to AC, it will simply tells us that B is equal to C. Similarly, if you have BA equals CA, it will simply tell you that B is equal to C. So this is the left cancellation. That means from the left of this pair, if you're going to cancel the left of this, you get this one. If you're going to cancel the right of this, you get this one. So this is just a basic claim that is actually playing a fundamental role in studying further with the group theory. So this one of the properties in the group theory that we have to encounter and we have to remember since we are studying with the group theory. So in this case, this is pretty basic to prove. If you have AB equals AC, observe that if I'm gonna multiply both sides by A inverse, that's gonna be here, and I have A inverse AC. So remember, this is E. So you have AB, and this is also EC. E is identity, so that means if you multiply identity by an element, that will still be the same element. So same is to here, you get C. Therefore, this will hold. So same happens with this. You just have to use the same method. You multiply A inverse both sides of the equation and you will arrive with the same answer. That's it. Number three, the inverse element is unique. So that means if you have an element in the G, in a group G, the inverse of this element is just 1. You cannot find any other inverse of that specific element. So let's assume otherwise if there's really another inverse aside from A inverse. So let's assume that A inverse is also an inverse aside from this one and this one. So let's go to that. For a given element A in G, since this is also inverse of this, so I can have A, this one. I'm sorry. And the binary operation is equal to the identity. But since this is also inverse, that means if I'm gonna multiply that, that will also be E. Okay? So this simply tells us that since these are all the same, so this will hold. A bar is equal to A inverse. But we have shown earlier the number two properties of group theory that the left cancellation holds. So if I'm going to cancel this, I would end up A bar is equal to A inverse. So therefore, this is just the same. So meaning to say, it only tells us that the inverse element of a group is unique. That's it. Okay, fourth property. The inverse of the inverse is actually that element. So meaning to say that if you have an element A in G, and remember this, this is the inverse of A. So the inverse of the inverse is actually the element. So to say on that, remember that I can write A inverse equals E. Okay? And also, if this one here, this is also E here. So, meaning to say, this implies that A inverse is the same as, I can also write this as A inverse, inverse, A inverse, right? So, I can also write this as A inverse, inverse, A inverse. So, by cancellation property we've done in number 2, I can cancel this, the right cancellation. So I have A is equal to A inverse inverse. So therefore, the inverse of that element is the element actually. That's it. Okay, so number 5. The inverse of the product of two elements is the product switch place of the inverse of two elements. So what does it mean? It only tells us that if you have two elements A, B in a group G, the product of, if you take the inverse of this product, you get the product switch place. So I'm gonna have B inverse A inverse of the inverses of two elements. Okay, so is this really true? So we'll see on that. Remember, what if I'm gonna multiply A, B, and B inverse A inverse? So what happened? Remember, we're working on a group, that means associativity holds. So I can associate this, and I have B inverse, A inverse, right? And remember, I can write this B inverse is the same as E. So I have A inverse. So if I'm gonna multiply this, I would have A. So I have A inverse. Why? Remember that the binary operation of an element to the identity is the same as the element. So the binary operation of an element and its inverse is actually the identity. What does it mean? It simply tells us that this is actually the inverse of this, right? But remember, the inverse of AB is this one. So AB inverse is the same as B inverse A inverse. That's it. Okay, so number 6, the last property. For every elements in group, you have, say you have A and B, the equations AX equals B and YA equals B have unique solutions in G. So that means you would have this one, and you would have this one correspondingly. So I'm gonna prove these AX equals B. So I'm gonna prove it has a unique solution. So remember that X, I can write that as EX. And EX, that's identity. This is actually the product of the inverse of I mean the binary operation of A inverse AX. So I can write A inverse, I have AX. Remember that associativity holds in G, so therefore I can do this one. This is valid. And this is A inverse. This AX is just B, so it holds in here. So this will tell us that it has a solution. Now suppose Y is also a solution. Oh, I'm not gonna use Y. I'm gonna use X bar instead. X bar is also a solution. So meaning to say that I would have um, a x bar that's the same as b, but that's the same as a x. So simply tells us that ax bar is equal to ax. Remember that we have shown this in number 2 that the left cancellation holds, so I'm going to cancel left of these. So x bar is equal to x. So that means it has a unique solution because they're actually the same. So same happens when we are going to show that this um, equation also holds for having a unique solution. That's it. Okay, so that's all for now. Thank you so much for watching. So if you have any questions or clarifications, you can comment down there so that we will know, and that way we can discuss your doubts or clarification for that. For those who are new to my channel, again, don't forget to subscribe so that you'll get updated on educational yet funny and exciting things about mathematics. So you can also comment there if you wish for a specific topic you would like me to discuss. Thank you so much, guys, for watching, and have a great day.